array-oriented programming with NumPy. In this lesson, we are going to focus on the NumPy library's data structure called ND-array, which stands for n-dimensional array. And one of the key features of this library and the ND-array data structure is performance. This library is geared to performance, and that is one of the key reasons why it is the foundation for something on the order of 450 other Python open source libraries that are available to you, including the Pandas library that we are going to be looking at later on this lesson as well. Now, as a part of this lesson, we'll be working with the NumPy module, and again, it is ND-array data structure. We'll talk about ND arrays are different from Python lists, and in particular, we are going to discuss the massive performance difference between them. ND arrays can be up to 100 times faster than corresponding operations on list objects from the Python programming language. We'll show you operations on both one-dimensional ND arrays and two-dimensional ND arrays as part of this lesson. And we will also demonstrate a whole bunch of common ND array manipulations. So throughout this lesson, we are going to be working with the numerical Python libraries array data structure. And the first thing that we need to do, of course, is to import the corresponding module, which is named NumPy for short. Now, per their documentation, they recommend that you use the as keyword and import the library shorthand as NP, and then use that to reference all the different functions throughout the library. So we'll go ahead and do that. And of course, one of the things we want to be able to do is create an array, and you can create an array object out of other array objects or any sequence or nested sequence as well. So I'm going to paste it in a snippet here, in which I have as an argument a list, a Python list of items 2, 3, 5, 7, and 11. The list is being passed to the array function from the NumPy module, and it is going to go ahead and create that array. And we can do things as we have done for other objects throughout these videos, like check the type of the object, so we can see that the actual data type is considered to be ND array, but yet you will often see them referring to that as array throughout the documentation. And of course, it's from the NumPy module. And just as we have done previously, we can go ahead and evaluate an array object to see what its string representation looks like. And I do want to point out a couple of things here. First of all, it does wrap whatever the contents of the array are in the word array in a set of parentheses in terms of the string representation. And then one of the things that you are going to start to see in this and subsequent example is that NumPy automatically applies formatting to the string representations of an array. So we'll notice here there is a space before the number 2. There is a couple of spaces here before the number 3, a couple before 5, and a couple before 7. So what's going on here is it's actually formatting every number to be the same width as the number with the largest number of characters in it. So 11 has 2 characters in it and space before it. So for 7 there is a space and 7, and then separately the space before it to separate it from the comma, and the same thing for the 2, 3, and 5 throughout the string representation. Now we can also, of course, create multi-dimensional data structures. So let me paste in the snippet that does that. As you can see inside here in the parentheses, we have nested list, a 2-dimensional list in which the main outer list contains 2 sublists. One containing 1, 2, and 3, and one containing 4, 5, and 6. If I go ahead and create that, and because I didn't assign the result to a variable, it goes and displays the string representation of that array. And notice that it's able to figure out that it's a 2-dimensional array that it needs to create based on the fact that it was a 2-dimensional list in the first place. So the first row of this new array we just created has 1, 2, and 3 in it. And the second row of the array has 4, 5, and 6 in it. In this part, we are going to take a look at various array attributes that help you learn information about an array object that you are manipulating. So once again, I'm going to import NumPy module as NP, and let's start by creating a couple of array objects. Here we have an integer array, which is a two-dimensional array with the three elements in each row. So we will create that and just take a look at it. And separately, let's also create our first floating point array object. So as you can see here, we have a one-dimensional list that we are handling it, and the values 0, 0.0 through 0.4. And if I go ahead and display that, you can see the formatting for a NumPy floating point array. And I do want to point out that by default, it does not show trailing zeros. So 0 point is how it represents 0.0 by default. Also, once again, it's going to format the floating point numbers with the same number of character positions to enable alignment in multidimensional arrays. Here we have gone here we have gone ahead and created a couple of arrays. Now let's take a look at what the data type is for each of these arrays. It turns out that for each array object, there is a D type attribute, and if you invoke that on the integers object, you can see that by default it has a data type called int64. Now this is one of many NumPy data types. NumPy is actually implemented in the C programming language for performance, and each of the types that you work with in the context of Python actually winds up getting mapped over to a C data type underneath the hood for performance reasons. Now, by default, when we are working with integers, we are going to get 64-bit integers underneath the hood in the context of NumPy. And similarly, if I go over to my floats and do dtype on that as well, you can see that we get 64-bit floating point numbers as well by default. Now I'm going to take a temporary diversion over to the documentation for NumPy. This page that you currently see displayed on the screen is where you can find all of the data type information for the underlying types that are stored in NumPy arrays. I am not going to go through this page in detail, but if you are interested in all the different data types that are available to you, you will want to go ahead and take a look at this web page. Let me switch back over to my terminal window. The next thing we want to do is take a look at how we determine an array's dimension. And it turns out there is another attribute that you can access for that purpose. So let's go ahead and use the ndim attribute, which stands for number of dimensions. And for the integers object, remember it was a two-dimensional array, so we get 2 as the result. And if I say floats.ndim, you can see that we do in fact get 1 as the result for that. You can also look at what they call the shape of an nd array. If I go ahead and say integers.shape and press enter, you can see that I get back is a tuple, which tells me how many rows and columns there were in that two-dimensional array. 2 rows and 3 columns per row, and again you can see 2 rows here, and each row has 3 columns. By the way, that's a difference between a NumPy arrays and two-dimensional lists. In a two-dimensional list, each row can have a different number of elements. In a NumPy array, all the rows have the same number of elements. Let's also look at floats array and look at its shape, and you can see we still get a tuple back, but it's a one element tuple, indicating the one-dimensional array has 5 elements in it. So when you are doing multidimensional arrays, you get the number of items in each dimension. So 2 rows and 3 columns for the integers array. But when you do a one-dimensional array, the tuple is a one-element tuple that has just the total number of elements in that one-dimensional data structure. The next thing we want to take a look at here is determining an array's number of elements and element size. If I say to the integers object, tell me what your size is, I get back 6, which is actually the multiplication of the number of rows times the number of columns. 2 times 3 gives me 6 total elements. And I can also go ahead and check the item size, which is how many bytes are being used to store each element in the integers array object. Now, in this particular case, it is 8 but this is actually going to be dependent potentially on the underlying C compiler that was used to compile the NumPy library in the first place. So we saw up above that we had 64-bit integers, which is an 8-byte integer, and therefore the item size returns 8 in this case. Now, of course, we can also look at the float array size, floats.size. There we go. And we have 5 as the total number of elements there, which is correct from the way we defined the array back at the top of the screen. And then separately, let's go ahead and check its item size as well. And you can see that the size for the items in the floats array are also 8 bytes each. And that makes sense because we had float 64 as the default type of that array. At this point, we have looked at the number of different attributes. I just also want to show you briefly that we can iterate through arrays just like we can iterate through lists. Let me paste in a snippet here first, and then we will execute it in a moment. Here we have a nested for loop that is going to walk through the integers array. For each row in the integers array, we are then going to iterate through every column within that row, and for each item that we are dealing with, we are going to display the column's value followed by a couple of space characters. Now, I don't really need to do this because if I just evaluate integers, it's going to give me a nice two-dimensional representation of the integers array. In fact, going back up here, we can see what that looks like, but let's go ahead and execute this. After the inner for loop ends, we'll just display an empty print, which will just output a new line character to drop to the next line and start the next row of output. So there's our 2 rows of output with the integers 1, 2, 3 in the first row and the 4, 5, 6 in the second. Now, one interesting thing that you may find the need for at some point is you can iterate through a multi-dimensional data structure as if it is a one-dimensional data structure. Let me paste in another code snippet here. We have the flat attribute of the integers object, and what that does is that it says to flatten out the multi-dimensional integers array. And in the case of integers, we had a 2-row 3-column array. What happens is that after the first row, it basically takes the second row and sticks it at the end of the first row for iteration purposes. Or if we had 10 rows and 3 columns, it would go row by row and just keep adding them to the end in terms of enabling iteration through the data structure. In this case, if I go ahead and execute the for loop, because I'm doing it through the flat attribute, it gives me back the integers as if they are just one-dimensional sequence of integers in this case. So far, we have created array objects by calling the NumPy modules array function and passing it a sequence of values, either a list comprehension or a predefined list object. In each case, in the preceding videos so far. Now, sometimes you will want to create NumPy arrays that have specific values in them, and they provide some convenience functions to help you do that. So, for example, I can go ahead and say use the NumPy zeros function to create an array of 5 zeros. And if I press enter, you can see it creates an array object. And by default, it gives me floating point numbers for the value 0. So 0 dot indicates that that's a floating point representation of the number 0. Now, there is also the capability to fill an array with ones for each of these different functions. There is also the ability to specify a keyword argument that indicates what data type the value should be. So in this case, up above, we got floating point values by default, but as we demonstrate the ones function, let's show you how to specify a data type as well. So let's say we wanted, instead of a one-dimensional array of 5 elements, a two-dimensional array with 2 rows and 4 columns. For that, we can go ahead and supply a tuple as the first argument that specifies 2 rows and 4 columns. And again, we are filling this array with ones, but let's say we want the data type to be integers instead of floating point numbers. In that case, we can say d type equals int, and now it knows that we want integer values, and you can see we get all ones as whole numbers without the decimal point following each of the different items in this case. And of course, sometimes you don't want zeros and sometimes you don't want ones, but rather just some value that you choose. So there is also a function called full. And let's say this time we want a 3 by 5 array object. And if we give it a value, in this case, the type of the element is going to be the type of whatever value you give it. So I'm going to get 13 as the result here, or as the element value here. And because 13 is an integer, I get all 13s throughout the 3 by 5 array and an integer representation. Next, we are going to take a look at creating ranges of values and turning them into arrays. Now, you may recall the range built-in function that we discussed at length in earlier videos. It was capable of producing a sequence of integers, and it turns out that the NumPy module has a function called aRange that works basically the same way and creates ranges of integers but turns them into array objects. So for example, I can go ahead and say call aRange with the argument 5, and that's going to produce an array containing the number 0 through 4, and you can see the result after I execute here. Now I can also specify the start point and the one past the end value. So if I say 5 comma 10, it's going to start from the value 5 and go up to, but not including the value 10, just as the range function does. And of course, you also have the ability to count backwards. So for example, if I do 10, 1 minus 2, you can see that we get all the values from 10. You can see all the values from 10 down to, but not including 1, decrementing by 2 each time. So the even integers from 10 down to 2. Now we also have the ability to create floating point ranges as well. So for that, let's go ahead and grab a snippet here and paste it in. We do that with the linspace function, and we have a starting and ending value in this case in the total number of values to produce. And if I go ahead and execute that, you can see it evenly divides up the range of values. And in this case, I get 0, the starting value, and then 0.25, 0.5, 0.75, and 1, the ending value produced as a result of calling linspace. The total number of items is 5, and you can count those up to confirm that. By the way, notice the formatting. So it's always going to align numbers based on decimal points. So if this were a multi-dimensional floating point array, we would see all the decimal points in each column aligned vertically, and again, it's always going to make sure that each value throughout the entire array in the string representation has the same number of characters positions. So we see 0 followed by several spaces and a comma because the widest of our numeric values in terms of the characters used to display them has 4 character positions. So 0 and a dot matches up the 0 and the dot here, and then there is a couple of spaces to be placeholders for the fact that there is 2 digits to the right of the decimal point in a couple of our numbers in the output. Now, another interesting thing that you can do once you know how to generate ranges is create a range of values and then turn it into a multidimensional array. That's known as reshaping the array. So take a look at the statement where we are going to create a range of values from 1 up to, but not including 21. So from 1 through 20, and we are going to take that into reshape the array into 4 rows and 5 columns in this case. So the result is going to be a 2-dimensional array with 4 rows and 5 columns per row, and you can see the values from 1 through 20 are laid out 1 row at a time in this new array that we just created. Now, one other thing about displaying arrays, as you start to work with big data, sometimes the amount of data you are going to be playing with all will be very massive. And by default in NumPy, if there are more than 1,000 elements to display in a given dimension, it's going to summarize the output, not display all of the items. So for that purpose, let's go ahead and grab a snippet here and demonstrate that we are talking about. So here we have a call to the arange function that's going to produce values from 1 up to, but not including 100,001. So from 1 to 100,000, we have an array that we are going to create, and we are going to reshape that into 4 rows with 25,000 columns each. So let's go ahead and execute that. First of all, notice it created 100,000 element arrays instantaneously. And second of all, you will notice that the array has 4 rows, but in each row, it shows only the first 3 columns and the last 3 columns. And it uses the ellipsis notation to indicate that there is a lot of elements, and therefore it is summarizing the output. And similarly, let's go ahead and change the dimensions here. So we'll do 100 and 1,000. And in this case, when we execute it, we see that we get summaries not only left to right within a given row. We see the first 3 columns and the last 3 columns. But in this case, we also see the first 3 rows and the last 3 rows as well. So a lot of different capabilities here. And one of the reasons that they do this again is because sometimes the data you will be playing with is so massive that you really can't just go ahead and display it on the screen. And there are always ways to work with the options provided by NumPy to control when the summarization capabilities kick in, and how many items should be displayed when summarization is occurring, etc. So that's beyond what we need to talk about here, but you can find all of those options in the online documentation.